And here at the Nvidia GPU Technology Theater, sponsored by HP, I have the pleasure of introducing Travis Oliphant, co-founder and CEO of Continuum Analytics, and he'll be presenting today on NumbaPro using Python using NumbaPro. Thank you, Travis.
Thank you, Allison. Well, it's a pleasure to be here for those here in person and also those attending virtually via the web. I'm excited to talk today about how we can use Python to actually accelerate applications on the GPU. My background, just a little bit about me. Let me see if I can get this clicker working correctly. So I started the SciPy project as a grad student, and that project has grown to about 2 million, about 1.5 million users now. And then had to rewrite NumPy in the middle of that. So I ended up spending a lot of time in the open source Python for Science community. And I've had a really great time interacting with all the people there. One of the things that's taught me is how there's a lot of people who want to do rapid development, rapid programming development. And so when they want to use the GPU, they want to accelerate their programs. One of the difficulties is they have to learn a new language. They have to learn C++, so they have to learn CUDA and some of the CUDA constructs. There's sort of multiple barriers to entry for many people who want to use Python, or who want to use science and accelerate that science with the GPU. I'm now at Continuum. The purpose of Continuum is really to promote domain experts and give them the tools they need to take advantage of modern hardware. We do have some products and services. You can check out our website. Wakari, Anaconda is a free Python distribution. But I'm here today to talk about kind of our big picture of trying to allow domain experts, scientists, geophysicists, domain experts of all kinds, people who are occasional programmers, subject matter experts. The GPU so far is pretty much only accessible to developer experts because you have to be a C++ developer or a CUDA expert. But there's a lot of people out there who want to speed up their applications, where their applications might just be some matrix multiplies, maybe some FFT, maybe some a simple workflow, and they want to take advantage of the GPU as well. And so that's what we're trying to do, is empower those people to take advantage with their scripts directly to hardware, both the parallel hardware that's emerging, both accelerators as well as multiprocessors, cluster machines. So that's what we do. I really promote array-oriented computing. Array-oriented computing is really the idea of organizing your thoughts into arrays or tables. Tables is a subset of that. And then expressing your algorithms on whole concepts, on large arrays at a time. Rather than writing a bunch of for loops, you want to write your algorithms at a very high level. And when you do that, you can get more done more quickly. And then you also can take advantage of hardware more easily as well. A lot of compilers do a lot of work to try to vectorize loops. Whereas if you have your arrays expressed already and the memory is already allocated coherently together, then your algorithms can be made much faster, more quickly, more easily. Clicker's not working. Okay, sorry, little technical difficulties. All right, there we go. All right, then, now a lot of people when they're doing acceleration, they don't think about Python. A lot of people think Python's a scripting language, it's not very fast, it's got problems. So I'm here to talk about how we've actually overcome those problems, and you can use Python to do accelerated programming very easily, actually. Why Python? There's a few reasons. It's a big list. I'm not going to go over all of them. You can sort of peruse at your leisure. Some of the big reasons are it's a free and open source community. It's a huge community of packages. So you want to be able to take advantage of those as well and link your hardcore optimized piece to the rest of it for display and for report generation, for all the nice tools that come with the Python distribution. It's got modern constructs, so it's a community that unifies not only domain experts, people who would otherwise use a domain-specific language like MATLAB or R, but it unifies those people in the Python for Science community with hardcore developers who are building just modern constructs on a modern language. Distributions of Python like Anaconda come with everything involved. Everything you need for science, technology, engineering, and math. Come with NumPy, SciPy, Matplotlib, scikit-learn, scikit-image. You can get a lot for very little. So that's why Python. Now, before I talk about NumbaPro, I have to introduce you to Numba, because Numba is an open source and free compiler for Python that really enables you to take Python code and run it on machine code. It creates machine code and runs it on the CPU. With NumbaPro, we've essentially just adjusted that, so now it runs on the GPU as well. So once you understand Numba, the concepts behind NumbaPro become much easier to understand. Basically, Numba allows you to have Python syntax but no GIL. You get native code speed for numerical kinds of operations, especially dealing with NumPy arrays. And we're currently developing Numba. It's still in development. NumbaPro is still in development as well. And Numba is built on the LLVM technology stack. So basically, Numba translates Python code. It uses a library on top of LLVM called LLVM-Py, and then constructs machine code out of it. And the nice thing about LLVM is I think it provides a very nice layer for different people to cooperate. Instead of using C as portable assembly, use a real IR as portable assembly, a real intermediate representation like LLVM as portable assembly, and everybody can cooperate. So this is what Numba does. It'll take a simple Python function and translate it. Uses decorator syntax, which just takes your function and returns to you something else. And the something else it returns to you is a Python wrapper to a native machine code function that does exactly the same thing. And here it illustrates how Numba takes this Python syntax function and generates portable assembly through LLVM that you can then call directly from Python. And that code is exactly the same kind of code you might create from a C++ compiler. So it really is no different. I like to show this slide to illustrate to folks, when you think about native performance, it doesn't have to be C++. It doesn't have to be Fortran. You can take Python syntax using Numba and generate the same IR that C++ would generate. Therefore, you can get native performance, native code speed. So it's really exciting because then you get fast development and fast execution. Now there's a lot of caveats there, but if you're doing NumPy style development with array-oriented syntax, it works really well right now, and we're making progress on actually supporting generalized syntax as well in the next release of Numba. This is the kind of thing you can do. With Python code, you can do a Mandelbrot simulation. So here's creating a fractal image. It's calling itself. It's calling you can see it's calling the Mandel function, which is itself JIT compiled. Therefore, there's no Python runtime overhead. It's going straight from the IR, basically C speeds, native speeds, to native speed implementation. So that can happen at real time. You can do real-time image processing with Python syntax. Now, the next step is let's take that. Great, you can read all about Numba. It's an open source project, numba.pydata.org. You can contribute to it. It's available for free download. I want to talk next about how we've taken that and made it possible to use that same style of high-level Python syntax and create GPU-accelerated code. So code that now runs on the GPU, and now your programs can be 2 to 15 to 20 times faster. So this is in NumbaPro comes as part of Anaconda Accelerate, which is an add-on to our Anaconda distribution. I'll actually show later how you can get Accelerate from any Python distribution using pip. But Conda install Accelerate, if you have Conda install, which is a package manager for Anaconda, gets you Accelerate, gets you a trial license, and then you can go to our website to find out how to purchase. But the purpose is to compile array expressions down to the GPU and let you run them quickly. So the NumbaPro also wraps up the CUDA BLAS, CUDA FFT, CUDA cuRAND, these libraries that do many of the things you typically do in numerical programming. It does it on the GPU, and you can then access those from Python very quickly and very easily. It uses NVVM, which is Nvidia's adjustments and additions to LLVM to allow LLVM IR to emit PTX code. And so NumbaPro sits right on top of that. It leverages Numba to generate the LLVM IR. And it has interesting constructs. So first of all, AutoJIT is sort of the standard wrapper. You AutoJIT a function, and then that takes what could include array expressions, meaning there's no loops in there. A, B, and C are arrays, and I'm essentially doing a simple operation with arrays and storing it in another array. There are no loops in there, but AutoJIT constructs native code that does the equivalent, does the needed routines. And you can even do different kinds of slicing and other types of expressions. So that's one thing that it provides. Also in NumbaPro is something called prange, which is really not necessarily for the GPU, it's for multi-parallel CPUs. Prange, it splits up the body of the for loop, compiles it into a separate block, and then executes that in a different thread. So it's OpenMP-like parallel execution from Python. Again, no GIL, it's fully serialized, fully threaded, using a thread that's completely outside the Python runtime. So it's sort of a way to get around the Python runtime. They still use Python syntax as needed. The way we really recommend using NumbaPro to begin with, to get things very, very quickly, this is the easiest way I know of to target the GPU and to write code that runs on the GPU. And it's to use a function called Vectorize. Now, Vectorize is basically a map function. You give it a scalar kernel, and then it maps that kernel over your data. And using Vectorize, this is using Vectorize just on the CPU. It illustrates how I can just create a simple sign function with an if statement. I can do whatever kind of code I want in that loop on scalar data, on elements. And then the Vectorize decorator constructs a function that will now take arrays and then apply that operation over the entire array. So Vectorize is actually available in Numba, and it gives you this NumPy ufunc. But the real interesting part, I think, is you can, with a single line of code, change target equals GPU, and now that code, it takes those kernels, spreads them across the GPU, and runs them independently on all the different threads, and now you can get parallel Vectorize. And so here's just an illustration. You can have a target equals GPU. You can target multiple CPUs as well. So instead of moving the code to the GPU, it moves it to just uses multiple threads to implement. And you can get very 5 to 15x speed ups just with a simple one-line code change. Just target equals GPU on your Vectorize functions. So this is a simple example. Here's you can do a benchmark on these sorts of examples, and you'll see the typical result, which is that there's some overhead in copying data to the GPU. And so you have to get to many millions of floats in this if you're only doing a simple amount of work each kernel, then you have to do a lot of work for it to justify the overhead of copying. You see that here. So the key is, as in everything, how do I do more work on the GPU with less data copying? And so one approach is just to do a bigger job inside the Vectorize. Here I'm using Vectorize to do that Mandelbrot calculation. So for each pixel in an image, I do this particular calculation, vectorize that. Now I can basically take a vector and do that Mandelbrot calculation on an entire vector and produce an image very, very quickly, having all of that work on the GPU with a single target equals GPU line of code. And then what we get in this, when you're doing a lot of work like this, you get 15x speed up. And here's a table showing you can do this in raw Python, of course, and get horrible performance. Once you use Numba, you can get CPU serial performance and then get 15x more once you use the GPU. Now, the other thing to do is to get more work done on the GPU is to take advantage of something called generalized ufuncs. And generalized ufuncs, rather than taking kernels that operate on scalars, they take kernels that operate on little arrays. So here's an example of writing a kernel that operates on an array and does matrix multiplication. So that kernel will take a single array, maybe it's a 5x4 array, and then it'll produce an output. But I might use it by taking 1,000 by 2x4 arrays. So I organize my code so that I'm actually operating. If I have a bunch of matrix multiplies to do, I put them all in memory, I create this kernel, and then just by calling that vectorized kernel function on larger arrays, it'll handle moving the data over to the GPU, doing all the calculations on all of the data, and then moving it back. And so you can get significant performance improvements using this. A little hard to get your mind around at first if you're not used to grouping your array multiplications together and then having each of them run and having a big parallel sort of generalized ufunc map over all those arrays. But once it's also not too difficult to understand how a 1,000 by 2x4 matrix multiplied by a 1,000 by 4 by x matrix, it does the matrix multiplication on the outer dimensions. So the 2x4 by the 4x5 creates a 2x5 result, and it does 1,000 of those, all on individual threads on the GPU. So very, very simply, you can build up calculations and get the kind of performance you're looking for that GPUs typically provide. Another approach is just to use the CUDA BLAS library. NumbaPro also contains library support for cuBLAS, cuFFT, and cuRAND. So you can just allocate data, access cuBLAS commands like gem, and do the matrix multiplication using the Nvidia provided libraries, optimized libraries. Here's an example that uses the FFT in order to do a two-dimensional convolution. Now the nice thing about this example is it illustrates how in Python you can write this code in a way that works for 1D, 2D, 3D, any kind of array operation. And the code is exactly the same. I have some arrays. I move those arrays to the device. I have an image and I have a filter on that image. And then on the device, I'm going to call the FFT in place and take the Fourier transform of the image, take the Fourier transform of the filter. Then I need to multiply them together. And I multiply them together using a kernel also targeted for the GPU. So that kernel then launches and does the multiplication on the GPU. So the FFT and the multiplication and the inverse FFT are all done on the GPU. And then the data is brought back. And in a very, very few lines of code, almost identical to what you'd write with NumPy anyway, you can do operations that are quite significant. And you get the same kind of performance improvements that you'd expect, somewhere between 2 to 6x, depending on exactly your hardware. Here's another example we've done that it's a Monte-Carlo pricer. It also illustrates using cuRAND to generate random numbers on the GPU. Again, most of the effort is trying to figure out how do I do more of the work on the GPU. And in this case, it's a simple Monte Carlo run. I'm just creating some random numbers, doing a simple pricing algorithm, very, very simple based on Black-Scholes. And then in this case, I use the Vectorize function to write the kernel. Notice the difference on the left-hand side. At the very top, my step function takes scalar arguments. So I vectorize that to produce an actual kernel that runs on all the elements of the array. On the right-hand side, you see a little more tuning, something using JIT. I actually formally use something called CUDA Python that I'll show in a second. I use CUDA syntax to actually take more control over the kernel that I'm writing and what actually executes over that vector. So that's on the right-hand side. But with these kind of operations, both will use the cuRAND to generate the random numbers. I'm just showing a difference between the kernels and how I might write those kernels differently to get optimized performance. And you can see that basically, by using parallelism and all the threads of the GPU, I can get 8 to 14x improvement. Very, very easily with Vectorize, I get 8x improvement. The big point is that this is easy to target the GPU. Suddenly, GPU programming isn't only available to the people that know C++ and have all this knowledge about how to manipulate and understand all the thread cores of GPUs. No CUDA experience necessary. You just understand this idea of mapping a scalar function over an array, and you target the GPU, and it works. So it's very, very easy to get stuff working. Things that work pretty well, they also give you the speedups. Now, there's also the ability to get deeper and write kernels that take advantage of all the performance improvements that CUDA provides. So you don't have to worry about leaving performance on the table if that's your concern. We have people who have used CUDA Python in production and are getting 85 to 90%, and in some cases even faster than their CUDA C++ code. So you're not leaving any performance on the table when you use CUDA Python. So here's an example. I'm not going to go into much detail about this because I really promote trying to encourage people to write at a high level, write their algorithms at a high level, and let the compiler take care of mapping it to the GPU. A lot of people are going to get much more performance that way long term, rather than having code you have to rewrite over and over again as the new tuning parameters come out. But in those cases where you do need more performance, you can get it by using CUDA Python and explicitly. You have to know some CUDA now. You have to understand a little about the threading, the thread blocks, the different architecture, the hierarchy that exists. But it's still fairly simple. You write a kernel in Python. That translates to a GPU kernel you can then call. Let's see how much time I have remaining. I guess a few more minutes. Great. So here's another deeper example with matrix multiply. This takes advantage of CUDA Python. Shows you have full access to things like the thread IDs and the block IDs. You have access to creating shared arrays. So many people who understand matrix multiplies on the GPU, the key is to do most of the work from thread local memory or from the shared memory near each thread. If you're trying to grab memory from the GPU global memory all the time, then you're going to have more latency and you're going to not take advantage of the optimizations that can occur. So this algorithm, doing matrix multiply, it's all really about just going from global memory to shared memory for each of the threads, copying that in chunks, and then doing the actual arithmetic from those shared memory locations. So if you get into the details like that, you can do it from Python. You can write CUDA Python code, construct a kernel that is going to be as optimized and as fast as other kernels you might write with CUDA C++ or CUDA C. Notice that also you can create streams, and then in that stream you can schedule different operations. You can schedule multiple streams, and you can schedule operations in those streams so they are happening asynchronously on the GPU while your CPU continues to run. So CUDA Python provides all these interfaces, so you really have the ability to control what you're doing. And you get about 6x improvement with this example. The opportunities are varied and wide. There are all kinds of opportunities for you to speed up your code. And we see in examples, in real-world cases, anywhere from no speed up because they're not doing enough work on the GPU, they're spending all their time copying data over, to 15x, even 20x speed up, depending on the kind of workloads and the way they can structure those. So how do you get NumbaPro? It's inside of Accelerate. So a couple of things to clarify. Numba is available open source. It's available in the free distribution Anaconda. Download it. It's available. You can play with producing serial code on your machine today. NumbaPro is available in the Accelerate add-on. There's a free trial. You can get it if you're a Conda user. Conda install Accelerate. If you're just a regular Python user, you can also get it by first installing Conda with pip install Conda, Conda init, then Conda install accelerate, and then you can get all the things you need to run NumbaPro on your Python distribution. It's also available inside of Wakari. Wakari is our cloud distribution of Python. Go to wakari.io and you can have a free instance running on Amazon clusters presently. We're looking to move to other cluster providers as well. But you can run your code with Numba. Numba's already there. NumbaPro's already there as well. Now, you won't be able to take advantage of the GPU features unless you run on a machine that has a GPU. But there are machines like that available in other clouds, and you can get Wakari and install it locally into your institution as well. So that's how you get NumbaPro. There are many examples inside of our open NumbaPro examples. Feel free to try it out. Academic licensing is available, meaning you can freely use it if you're an academic from an education degree granting institution. And if you're at a research institution, call us. We can give you a 1-year free version of NumbaPro or Accelerate to try out. So it's easy to get, easy to use. There's a list. Give us feedback. We'd love to hear from you. And I'm open for questions.
Great. Thanks a lot, Travis. Do we have any questions here in the theater?